Now that we have the training, validation, and test data sets for link prediction, let's set up our graph autoencoder, and you'll find that this is fairly straightforward, especially once you've understood the concepts that we've discussed earlier. Let's first talk about how this autoencoder will help us with link prediction. We'll use the encoder portion of the model that's defined in the encode method here to generate embeddings for every node in our graph. These embeddings will, of course, use message parsing to include local neighborhood information. The decoder portion of the autoencoder, which is defined using the decode method, will try to reconstruct or generate the adjacency matrix of the original graph, and it'll try to predict those nodes where connections exist and those nodes where connections do not. The decode method will recreate the adjacency matrix for only one batch of data that we parse in. Decode all will create the adjacency matrix for the entire graph. This autoencoder works on the following premise. If the embeddings for two nodes are very similar to one another, then it's quite likely that an edge exists between those two nodes. That is, one scientific publication cites another. If the embeddings of two nodes are far apart or dissimilar, then no edge exists between those pair of nodes. With this big picture understanding, let's take a look at the details of this autoencoder. The init method takes in the number of in-channels, hidden channels. In channels here is equal to the number of features for each node. For this particular Citeseer graph, we know that every node has a feature vector of size 3703, and this feature vector indicates the presence or absence of words from a predefined dictionary. Hidden channels represents the number of unit in the hidden layers of our graph convolutional network, and out channels represents the dimensionality of the embeddings that we generate for each node. These embeddings for a node will represent the node features and the interconnectivity of that node within its local neighborhood. The encoder portion of this autoencoder is made up of two graph convolutional layers instantiated on line 6 and 7. Let's look at what a forward parse through the encoder looks like. We take in X the node features, an edge index that is the message parsing connections, and parse those through the first convolutional layer followed by ReLU activation. This output is then parsed through the second graph convolutional layer, which generates the latent space representations or the node embeddings for every node in the network. Now, the decode method makes up the decoder, and this uses the node embeddings generated to predict whether a link between a pair of nodes. Now, we use the inner product for link prediction. The input Z contains the node embeddings for the entire graph, and we use the edgy label index to look up the node embeddings for every node pair. Notice on line 16, we compute the inner product between the two nodes' embeddings. The node embedding is just a vector, and the inner product measures the similarity between two vectors. It helps quantify how similar or related the two nodes are based on their learned features. Nodes that have a higher value of the inner product are closer together in the embedding space and are more likely to be connected. Decode all is simply a decoder for all nodes in the graph. You can see on line 19, I used the matrix multiplication operation to compute the inner product between every pair of nodes in the graph. This will give us unnormalized scores representing the likelihood of an edge between every pair of nodes. And I invoke the sigmoid function on probability adjusted to get normalized scores between 0 and 1. Probability adjusted on line 21 will contain values between 0 and 1 for the adjacency matrix that we have generated for the graph. The closer to 1 a particular value in this adjacency matrix, more likely there is an edge connecting the two nodes in that graph. Notice that I perform a thresholding operation to only consider those values in the adjacency graph where the probability score is greater than 0.99. So in the adjacency matrix that we return, we'll only have values of 1 for edges that are very, very likely. Now that we've set up our autoencoder for link prediction, let's instantiate the autoencoder. You can see that the input channels is equal to num features. I've chosen 128 as the hidden channels dimension, and out channels equal to 64. The out channel represents the latent space embedding dimensions for the nodes in our graph. We use the atom optimizer with a learning rate of 0.01, and the loss function is the binary cross entropy with logits loss. We use BCE with logits because the decode function that we use for model training returns unnormalized probability scores. It does not return normalized scores. BCE with logits combines a sigmoid layer and the binary cross entropy loss. Now, We haven't trained our model yet, but let's just see what the output of the encoder looks like. I'm going to call model encode on the X features and the edge indices of the training data. And here is a sample output of the encoder. If you look at the shape of the data, the embedding representations of the individual nodes, you can see this is a matrix of size 3327 by 64. Every node has a latent space representation of dimensionality 64.